Hello everybody, my name is Jack O'Connor and I'm a PhD student at the University of Cambridge under the supervision of Tom Gurr, and I'm going to talk to you today about perfect zero knowledge PCPs for Sharp P, which is some joint work with my supervisor Tom and also with Nick Spooner, who's at NYU and the University of Warwick. So I'll get stuck straight in. So the first thing I'm going to talk about is PCPs. We're talking about zero knowledge PCPs, so we're going to quickly refresh what PCPs are. So PCPs are probabilistically checkable proofs. And what does this mean? Well, we are going to think about a setting where we have some verifier algorithm, some polytime verifier. They're going to get as input some input X, and their entire goal in life is to figure out, to decide is X in the language L or not. That's their entire purpose. And we're going to give them access to a proof. And we can think about this, you can this is a bit analogous to like an NP proof or like an NP witness. And in that setting, the proof is poly-length and the verifier kind of can take it as input. But here we're going to think about giving the verifier access to an exponentially long proof. For this talk, that's kind of the way to think. And the verifier has access to an exponentially long proof. So rather than getting it as input, it's going to get like an oracle to this proof. We're going to kind of ensure the verifier can use this extra proof length we're giving it. We're going to give them some randomness. So we'll give them some coins to flip or dice or whatever. And what's going to happen, the verifier is going to use its randomness. It's going to query this proof in some location. So it has like an oracle to this proof. And then it will kind of query it in a bunch of different locations. And ultimately it will either accept or reject. And we kind of want this PCP or this proof to make some sense. So we have a couple of guarantees we'd like. The first is completeness, which is just kind of saying that if you get a valid proof for a valid instance, then the verifier accepts with high probability. So if X is in the language and you get a valid proof, you should accept with high probability. And we also want a soundness condition, which basically just says that you shouldn't be duped. So if X is not in the language, then no matter what proof you get sent, with high probability you'll reject. The verifier will reject. Okay, so a couple of kind of complexity measures that we care about in this setting are the randomness complexity of the verifier. So that's just how many random coins the verifier needs to flip to perform its verification. And you can think this is really a proxy for the proof length. Really this kind of controls the proof length, which is we want this to be small. And we also want the query complexity to be small, which is just basically how many queries that the verifier needs to make to the proof in order to verify the proof. Great. Okay. So now I'm going to shift gears slightly and just very, very briefly talk about zero knowledge proofs, which are kind of the other components of zero knowledge PCPs. So, it's I guess given that Avi is accepting or giving his Turing Award lecture at this conference, it's worth quoting the title of his paper. There are proofs which yield nothing but their validity, which is exactly what they are. So the verifier, you're going to again have a verifier, they're going to get some input X and they want to decide if X is in the language or not. And we kind of want them to learn nothing more than that X is in the language. So they're going to interact with some prover algorithm who's also going to get X's input. The verifier is going to use some randomness because you can show that if the verifier doesn't have access to randomness, you kind of can't do any, you can't have zero knowledge proofs for anything more than BPP. Both parties will send a bunch of messages back and forth, and ultimately the verifier will accept or reject. And just like before, we want completeness, we want soundness, we want these kind of same conditions, but we also want this zero knowledge condition, which we formalize by asking for a simulator. So, we say there's a simulator which gets the same powers as the verifier, so access to X, the input, and randomness, and also runs in polytime, and it ought to output, what the verifier sees. So what does the verifier see? Well, in this case, it sees all the messages in the protocol, so N1 through MT, and it also has its internal randomness. So the simulator needs to output basically something that's distributed very, very closely to M1 through MT and the randomness. And if these two things are distributed, if the simulator's output is distributed identically to the messages and the randomness, then we say we have perfect zero knowledge, which is kind of the main thing we're going to talk about in this talk, or we're going to be concerned about in this talk, because spoiler, it's in the title. And And the only other thing I want to mention is that we want that even if the verifier is Dick Dastardly and does all sorts of funny things or tries their absolute best to learn something from this protocol, they still can't. There should be a simulator algorithm basically for every malicious verifier, which can output its view no matter how it kind of misbehaves. So that's kind of the background. So what are zero-knowledge PCPs? Well, it's pretty easy to explain with that stuff out of the way. They're just PCPs that have a simulator. So the verifier, on interacting with the proof, or on kind of inspecting the proof, I should say, shouldn't learn anything more than the claim that X is in the language. And we formalize this by asking that there is a simulator. So what happens in the real protocol? Well, in the real execution of the protocol, there's a proof written down. The verifier gets an oracle to this proof. It gets its input X. And it rolls some dice or flips some coins, and ultimately, comes up with some bunch of queries that it makes to which we'll call Q, which it makes to the proof. So what does the verifier see? What's its kind of view of the whole protocol? Well, it sees its internal randomness, and it also sees the proof restricted to Q. Okay, so that's everything the verifier sees. So then we want a simulator that can that can output the same thing. So under the assumption that we're in the honest case, like that the proof is an honest proof and X is an L, otherwise it doesn't make sense to ask for a simulator, we basically want there to be a simulator, which is going to get as input X. It's going to have the same runtimes as the verifier, the same powers as the verifier. So it's going to have some randomness, it's going to be poly time, and it's going to have to output something that output the view of the verifier, right? And for this to be perfect zero knowledge, we're going to basically ask that T is distributed identically to pi at Q, restricted to Q, and the randomness, the whole thing, should be distributed identically, not just T. But there's a couple of things. So you might be kind of wondering why I'm talking about randomness in terms of the queries to pi, but I'll get there. So there's a couple of things I want to mention. First, I want to say that, like before, even if the verifier is an evil mastermind and tries to learn whatever they can from the proof by querying it in all sorts of ways that weren't prescribed in how it's supposed to inspect the proof, we still want there to be a simulator which can output the verifier's view of the proof. So they're just like before. So we want to be able to handle malicious verifiers. But the malicious verifier needs to be kind of query bounded, because if they could read the entire proof, say, I think about like the NP case, like if you're trying to write down a PCP for NP, the PCP kind of necessarily encodes something about the witness. And obviously if the verifier can read the entire proof, then they kind of should learn something about the witness, which wouldn't be zero knowledge. But throughout this talk, the proofs will be exponentially long and the verifiers will be poly time. So the poly time is the query bound on the malicious verifier. But the more kind of subtle point is that the proof itself needs to be chosen randomly. And this is because if you don't have a randomly chosen proof, then you kind of can't hope to get zero knowledge for anything more than trivial languages like BPP. So this is kind of in contrast to what we usually think about PCPs. We think about like some fixed encoding, fixed deterministic encoding for each instance. Now you can think about the encoding as being randomized, or you can think about there's like an ensemble of proofs, or not an ensemble. It's like there's a collection of proofs and there's some distribution over those for each instance. And when you're writing the proof down, you just pick one of those according to that distribution. That's basically everything about zero-knowledge PCPs. And I'll quickly basically say that this is the full definition. So I'm not really hiding anything. Like everything I've just talked about is exactly what's going on. So we just basically ask for a PC, or we say a PCP is perfect zero knowledge if we have this simulator, which can handle, which is able to, for any malicious, even adaptive verifier, is able to output its view. And by view, I just mean the randomness and the set of queries, the kind of query responses that it would see. Okay, so before I talk about our work, I'm just going to quickly mention some prior work. So there's two lines of work I want to talk about. The first one is was initiated by Killian, Trank and Tardish in 1997, and they basically constructed statistical zero-knowledge PCPs for NEXP and also for NP, which I'll throw up as well. So this is a really nice line of work. They basically, in the NEXP case, they're secure against all polytime malicious verifiers. In the NP case, they kind of can fix any polynomial. When you write the proof down, you fix a polynomial, or a polynomial number of queries which you're secure against. But there's kind of two comments I want to make on this. So the first is that the zero knowledge is statistical, and this is inherent to the construction and the way they go about it. And also the honest verifier will be adaptive. So even though the kind of, whenever I'm talking about adaptivity, the malicious verifier is always adaptive. But in this case, even the honest verifier is adaptive, and we would obviously like the honest verifier to be non-adaptive. And additionally, and this is also inherent to the construction. So both the statisticalness and the adaptivity of this result are inherent. And then the second line of work is more cryptographically motivated. So this is by like Yuval Shai and Weiss and others. And they're trying to basically come up with statistical zero knowledge PCPs for NP, where they get rid of this adaptivity. They want to have an unadaptive verifier. And they do manage to do this, but it comes at a cost. So either they only obtain witness indistinguishability, or they only get a quadratic query gap. And by a query gap, I basically mean the number of queries the simulator can handle less the number of queries that the honest verifier makes. So it's kind of how much more secure you are than your honest verifier. And in this this means basically you only get a quadratic gap, which is obviously not super strong. With that out of the way, I can talk about our result. So our main result is the following. We proved that there are perfect zero knowledge PCPs for sharp P, and these PCPs have the two parameters here are poly-poly, so there's poly randomness complexity of the verifier and poly query complexity for the verifier. So this is like an exponentially large proof, basically, that the verifier makes polynomial many queries too. And how do we do this? Well, at a really, really high level, we show this by constructing a perfect zero knowledge PCP for a decision variant of sharp-SAT. So this is just basically, you rather than kind of it being a function problem, you think about it as a decision problem, and you kind of you have a CNF and a number, a natural number pair, and if the natural number is the number of solution or satisfying assignments of that CNF, then it's in the language, otherwise it's not. So we construct a PCP for this language. That's how we do it. So the next thing then is just some comments about the result. So this is the first construction of a perfect zero knowledge PCP for any non-trivial language, which is like this. So, if you remember, previous constructions were statistical zero knowledge rather than perfect zero knowledge. So this is the first kind of known perfect zero knowledge PCP. We also achieve non-adaptivity of our honest verifier. And if you recall, the previous constructions, one line of work was kind of inherently adaptive, and the other line of work paid for their non-adaptivity. But we don't really pay for it in that we get we get full perfect zero knowledge against arbitrary polytime verifiers, so any polynomial time malicious verifier, including adaptive ones. And lastly, our result is entirely unconditional. There's no cryptography or one-way functions or any assumptions lurking. This is completely unconditional, which is quite cool, I think. So for the last 10 minutes, I'm going to quickly talk about how we go about getting this result, we'll get stuck into that now. So I'm going to start by reviewing the sum check protocol very quickly. So hopefully you can just recall the fact that we can use sum check to we can use the interactive proof sum check to decide the sharp-SAT language that we mentioned a couple of slides ago. So we're going to take our CNF, we'll encode it as some polynomial, and we call that f here. I'm just going to go through it for like a two-variate case just to quickly recall it. So we'll have how this works. We have some verifier. The verifier is going to have oracle access to the function f. And it's going to interact with some prover. So this will neither be zero knowledge nor a PCP, but we're going to kind of work towards that. How will this work? Well, the prover will send in every round a univariate polynomial. And in the first round in particular, it will send this one. So what are these univariate polynomials going to be? Well, they're going to basically be subcube sums. So in particular, in the first round, the prover will kind of, sum over everything apart from the first variable, all the variables apart from the first one, and leave the first one free for the verifier to input this polynomial. And they'll send that polynomial to the verifier. And then, the verifier will perform some check. We're not really super concerned about the checks here. We know there are some checks that are going to work. I'm just going to kind of recall the most important thing is the prover messages. the verifier is going to make some random challenge, and then the prover is going to send, another polynomial. And this one now will be the next subcube sum, where we fix the first entry to be the verifier's challenge, and then we let the next entry be free, this x, and then we sum over everything else. But since we're in the two varied case, we're kind of finished, and there's no sum anymore. And the verifier is going to check that this final polynomial kind of agrees with f, so they make one query to f, and check in a random location that these things agree, and then they'll do a consistency check between all the rounds. And we can generalize this to to an m varied polynomial, where we're going to just have extra rounds for each each variable. So the important thing here is that we can write this as a PCP. So hopefully we're all happy that sum check works, and that this is an interactive proof. But now we're going to turn it into a PCP. So how we turn it into a PCP? We'll kind of do a common trick. We'll get the prover to write down every possible answer that they could ever write in an honest execution of the protocol, and they'll write down this. This will be like an exponentially big proof. And what will it consist of? Well, it'll consist of, like I said, all the possible answers. So the verifier will be able to, when they're querying this proof, you can kind of pick what length you want your input to be, or your query. So you can kind of you could query C1, just C1. You could query C1, comma C2. You could query C1, comma up to M. So you can make any length of query, and what that query corresponds to in the honest case is basically fixing the first I entries to be C1 through Ci, and then summing over the remaining entries. Okay, so it's kind of it's what the prover will send you in the ith round, but and then you plug kind of Ci into that thing they send you. So it's going to give a more concrete example. If f is 3 variate, then you could plug in C1, comma C2, and then you would fix C1 and C2 like this, and just be summing over the last entry. Or you could you could just fix the first entry to be C1, and then sum over the final two entries if you're in a 3 variate case. So the point is, this is enough. Access to this is enough to run the sum check protocol, but this is not zero knowledge. So this is our PCP, and we're going to try and make this PCP zero knowledge. Okay, so the kind of gist of the idea is to use a random mask, and this was used in the past in BCFGRS 17, where you basically take some random low degree polynomial and add it on to f. And the idea then is that this will kind of mask the subcube sums that the verifier normally has access to when you do the regular sum check PCP. But for soundness, if we're just forgetting zero knowledge for a second, we need that the sum of this polynomial we're adding on is 0, so that the whole overall sum is preserved by this masking. Okay, so maybe you would think, okay, we'll send a PCP that the sum of f plus r is whatever the input is, so is gamma, whatever the input is, and we'll send a PCP that the sum of r is 0. But this doesn't work, and the reason it doesn't work is because if you query the proof for the sum of r and the proof for the sum of f plus r in the same location, and then subtract the two responses from one another, because everything is linear, the r's cancel and you can recover the sum of f. So you can get any subcube sum of f you want. So this doesn't work. So we need to do something a bit more clever. So kind of to summarize what we actually really need. We need that the full sum of r is fixed, of this masking is fixed, and in particular we kind of want it to be 0. And we also want that any of the subcube sums, so if you were to make any kind of sum where you don't sum everything, but you you fix the many elements and sum the rest, we want to hide those, because they require exponentially many queries basically to f to compute. So the verifier couldn't possibly compute them, so it wouldn't be zero knowledge if they learned them. So our idea is the following. It's that reversing the order of the variables would preserve the full sum, but it won't preserve the subcube sum. So what do I a Well, if we take a polynomial q and we sum it from b, we put the variables in b1 through bm and sum over everything, clearly that is equal to the sum of q, where we've reversed the order and gone bm minus 1 all the way down to b1. These are the same. But if we were to then take a subcube sum where we fix some entries like C1 through Ci, and now we do the reversed sum, these two things are no longer in general equal. And a good analogy to bear in mind here is it's kind of like taking a matrix and summing the entries. So if I sum all the entries in the matrix, it doesn't matter whether I sum the columns first and then add those answers up, or sum the rows first and then add those answers up, we'll get the same thing because we're summing everything. But if we were to just sum, kind of just take one column and sum that up, or just take one row and sum that up, we wouldn't expect those two things to be the same. That's kind of the analogy that's going on here. So this is kind of the core idea of the proof. So this lets us basically define R in this way. So we define R to be a uniformly random low degree polynomial minus the kind of reversal polynomial, where we flip the order around. And now, by definition, we'll get this soundness guarantee that the sum of R is 0. So like structurally, R has this property that makes it be 0. Rather than us having to prove that R is 0, by definition of how it's going to be supplied to the verifier in terms of this as this Q, it will sum to 0, which is great. So we get soundness. And we also want a zero knowledge guarantee, right? So we kind of need to again show that all these subcube sums are hidden are masked by this choice of R. So if we just think for a minute on the hypercube, just queries where you can set your C's to be zeros or ones, which is kind of the kind of we'll just think about that setting to simplify things. Then certainly this is the case, right? That we're going to mask them because by what I said on the previous slide. This sum will not be identically 0 for all Q unless you're either summing, everything, which is the previous case, the soundness case. That's input to the problem, so we don't mind. Or if you are summing, if you're fixing absolutely everything, so you fix C1 through CM and you pick C1 through CM to be something that's a palindrome, then this will be 0. But otherwise, in general, for all Q, this won't be 0. So it turns out to be something uniformly random, which you can show that, and that lets you prove that you're basically able to mask quite well. Okay, so there's one more thing I need to mention before we kind of just talk. We see the full construction of the proof, and that's that we've given R some additional structure. So before R was kind of the original idea was to have R be as random as possible, and then we kind of said, well, we need to give something up here. We need to kind of introduce some structure to ensure that R sums to 0 on the hypercube. But it has more structure than that now. It doesn't just have this thing where it sums to 0 on the hypercube, but also if you look outside the hypercube, remember R is like some polynomial over this field, so you can query it in other locations. It has this what we call anti-symmetric property, which is just what's on the slide here, and this means that maybe it leaks into some information. So if we want to simulate, we kind of want to try and reduce. We want to make things as random as possible, as random as we can. So we want to try and reduce how much structure there is. So we make the following modification. So we define R to be the same thing as before, but we kind of tack on this extra term at the end. So what is this extra term? It kind of looks a bit scary. This term really is just a uniformly random low degree extension of the all 0 function on the hypercube. So you set for all 0, 1 points, like the hypercube, so 0, 1 to the m, you set everything to be 0, and then you take a low degree extension of that. This extension will not be, you won't be taking the unique extension. We're thinking about the individual degree being at least 2 here, so there are lots of different extensions, so you pick one of them uniformly random. And for our purposes, the combinatorial Nullstellensatz of Noga Alon gives us basically a way to write this this polynomial, this random low degree extension of the 0 function. Basically, if you look at this, you can see that the x times 1 minus xi thing is going to be 0 if you plug in all zeros or all ones and zeros. If you plug in binary strings, and then these ti's are just themselves uniformly random low degree polynomials. So when it comes to simulating and writing the proof down, this makes life quite a bit easier. And this is going to be our final choice of masking polynomial. So we're happy. So this is the full construction of the proof. I'm not hiding anything here at all, actually. So what do? We sample Q, like I mentioned, and we write down the full evaluation table of Q. And then we sample all of these TIs, which are so there's m of them, one for each variable, and they're all also just low degree polynomials. We write down their full evaluation table. Then we define R as before, and we write every subcube sum of f plus R and output all of those proofs. And that's the entire construction. I should say before we finish that most of the technical work in the paper is actually in writing down the simulator. So you have to be able to simulate queries to this proof, which is really involved, and there's lots of very, very nice ideas involved with kind of being able to kind of lazily sample polynomials and subcube sums of polynomials, and also handling this anti-symmetric structure which remains on the hypercube even though we've got rid of it everywhere else. But I'll just encourage you to read the paper, and thank you very much for listening.